Ladies and gentlemen, this is Professor Ramesh Malla from the University of Connecticut. I would like to recognize my co-authors, Celso de Oliveira and Santos Dacal. They are my graduate students working on this project. Today, I'll be presenting some of the results from the research we did on railroad bridges monitoring and modeling. As for the background and significance of the works we have done here, I think we all know the importance of railroad transportation system for the economy of the nation and the regions. It should suffice to say that in the New England region, we have a NEC, that's the busiest passenger line, and also there are numerous bridges which are more than 100 years old. So there is importance that we will study the health monitoring technique for this kind of bridges for their durability. The objective of this study is to develop efficient, cost-effective methodology for accurate response determination and health condition monitoring of existing railroad bridges using field testing, finite element modeling, and material characterization. Today's presentation, I will be presenting some of the results in these aspects of research. We have investigated in detail two bridges in Connecticut. One is Devon and another is Cosco Bridge. Today, due to lack of time, I will be presenting some of the results only in Devon Bridge. Given on this is brief information on Devon Bridge, one of the two bridges we have studied in detail so far. Devon Bridge is over Housatonic River between Milford and Stafford in Connecticut. The bridge was built in 1906 and owned by Connecticut Department of Transportation. The bridge has 7 spans and total length of the bridge is 1,067 feet. And the span we studied is the eastmost span. That span is about 218 feet long. And as you see here, we have shown the schematic as well as 3 pictures of the Devon Bridge. Shown here are the 3 passenger trains which are typically run over the Devon Bridge. The left is Metro North, the middle is the Amtrak Regional, and the right is Amtrak Acela. The Acela has engine rear and front, and the Amtrak Regional has engine only at one end. And Metro North trains don't have engine as they run in electricity. Now I will present brief information about the field test of the railroad bridges we have studied. This slide presents the instrumentation we use. On the top, this is the concept of laser Doppler vibrometer, which uses Doppler effect to find frequency shift and then determines the velocity. And this is a non-contact sensor. The another type of device we use was the accelerometer. Piezoelectric accelerometer that is attached on the bridge to measure the acceleration. I would like to present the test setup on Devon Bridge on this slide. As you see in the top, we see a truss, one of the 2 trusses on span 7 of Devon Bridge, and the red dots are where we measure the velocity of the bridge with the help of laser Doppler vibrometer, and the green dots are where we attach the accelerometers. Now the picture down show the setup, the laser Doppler vibrometer setup. We throw the beam from laser Doppler vibrometer directly upward on the bridge, and the reflected beam is measured or collected to get the velocity. The information presented on this slide gives the essence of the time domain analysis of the field collected data. The results here are collected under Metro North train going in the direction of the red arrow shown here, and the red dot is where the velocity of the bridge is measured, and the green dots are where the accelerometers were placed. On the left side, you see 4 diagrams. The very top left is raw data collected. To the right of that is center data. The axis is shifted up to align with the x-axis, and the bottom left is the data after the low pass frequency to get it to unwanted frequencies, and the right one is the actual final displacement curve. So the velocity, as in LDV measures velocity, and that is integrated to get the displacement. And on the right side you see the acceleration. The top one is the acceleration obtained by converting the velocity given by the LDV, and the bottom two are the measured acceleration from the accelerometers, and they are pretty close to each other. Shown on this slide is the frequency domain analysis of the field measured data. The left side is the data we collect in the field, and that data is processed using the fast Fourier transform to get the information as shown on the two diagrams at the right side. The top one is the response when the train is still on the bridge. This keeps, as you know, there are a lot of peaks here. Some of them are related to the axle frequencies. Some also has some natural frequency here. The bottom one is the data process after the train leaves the span, the particular span 7. That's the free vibration. Even though the train is off the span, the bridge still vibrates sometime. So that gives us the natural frequency. So this diagram will give us natural frequency and the axle frequencies. The additional advantage of the field data collected, we have discovered, is that we can even get certain parameters concerning the trains, the vehicle going over the bridge. As you see here on the left side is the displacement we got from processing the field measured velocity from the laser Doppler vibrometer. Now, if you count these peaks, up and down peaks here, these are all given by the axles. We are measuring, as you know, velocity at a certain point, and when the axle comes there, the displacement would be larger, and axle goes up the point, displacement will be lower. So if you measure the peaks, these peaks give very good idea of how many cars the train has, and how many cars, and of course, if there is an engine, then engine also there, right? The peaks will give that information, number of peaks. The other thing is measuring the time between the two peaks and the distance between two axle system, two consecutive axle system. From there we can get the velocity of the train. So if you divide the distance between two axle system with the time from these two consecutive two peaks, you're going to get velocity, and that's exactly what we have shown in this table here. And for this case, the velocity 41.78. So we get two very good pieces of information about the trains. Now let's go to finite element modeling. We did extensive finite element modeling. I'm not showing here many detail here. It's a complex process to generate finite element modeling of these kind of bridges. We started from our shop drawings, got all the geometric parameter from the area, moment of inertia. All composite section is a little complicated. And then we apply the train loading, as you see here. The axle of each train, axle load, we consider as a triangular pulses. Now you will see all these spikes given by each axle load. And if you look at on the bottom on the right hand side, the first one is the metro north, and as you see the amplitude or magnitude is very much equal here because all cars are same metro north. Now the second one here, as you see here, very beginning, there are two axle system there, front and rear axle system of the engine. So the magnitude larger than the cars here after that. Now if you go to the bottom diagram, there are two engines, the front side and the rear side. So the magnitude there of the axle loads are much higher than the in between, which are the cars. We're trying to show the comparison between the field and the finite element. On the left side are all these field collected data. We did the FFT, the fast Fourier transform, and on the top and bottom is the PSD, the power spectral density curves. Those are from field and from the field data collection. It's not directly in the data collected in the field, but after collecting the data, we had to process. And on the right side is the more steps obtained from the finite element model. And the left side bottom, here we are comparing between displacement from the field with the red curve and blue curve are from the finite element. They are not exactly the same, but very close, at least in the qualitative form, similar ups and down. And now in the table down on the right, we are comparing the frequency. The first natural frequency, lateral frequency, the second lateral twisting, longitudinal. They're very close. I would say the second and third very close. The first one also not that bad. 1.4 versus 1.78 from the field, 1.4 from the finite element. What we did, we collected some material thanks to Metro North. They provided us material from the Coscoff Bridge and the Devon Bridge. We got them, cut them out from the big pieces we had, and we use the ASTM standard to make the specimen, as shown geometry on the top right. We use our machine, tensile testing machine. The top one is the Devon bridge result, and bottom is the Cos curve. The left side, we did 3 samples testing each of them for each bridge. Left side is the total one from starting to end. The right side diagram is the blown view of the initial region. Pretty good. It's a very good curve we got. Now yield stress more or less same as the original steel. That, by the way, these bridges are made of A7 steel. Only thing we saw is a little bit decrease in the ultimate stress, but I think mainly for design we use the yield stress. So as far as the material concern, they look pretty fine. Uh, Now, summary and conclusion, again, shortage of time here, lack of time, I cannot go into detail, but just to summarize, as you saw here, we studied the dynamic response of our bridges under the service load, Amtrak XLI, Amtrak Regional, and Metro North, and we computed natural frequency, mode states, displacement using both finite element as well as the field data collection, and we collected field data from 2 different kind of instruments, laser Doppler vibrometer and accelerometers, and also did try to characterize the material using the tensile testing. So these information should be very valuable for practicing engineer to process the data first, and next is okay to get some idea or assess the condition of the bridge. There are some differences in field and collected and the finite element model data in a displacement on the Devon bridge. I think that we are looking further into that, the cause for that. Slide. Finally, I will go for acknowledgement. We got a support from quite a few organizations and quite a few individuals. We are very appreciative of their help. First of all, USDOT, University Transportation System, TIDC, providing partial funding for this project. Conduct and Metro North been very much instrumental, providing us the bridges, helping us in all the logistics for field testing and the support needed for those purposes. Polytechnic, as we greatly appreciate their help, and they provide us the laser Doppler vibrometer for collecting data, and also they came and help us on a bridge testing using their 3-dimension laser vibrometer. Amtrak and Genesee in Wyoming giving us comments and feedback, and Amtrak generously also provided us the information on the trains. Main DOT, we appreciate providing us the material from their bridge. As a matter of fact, I didn't present all the results here, but we have tested material from a total 4 bridges, 3 from Connecticut, 1 from Maine. And New Hampshire DOT for providing us the bridge to analyze for the critical memory and critical connection. 9, we also like to thank Western New England University providing their lab, making their lab available for our tensile testing, some of our tensile testing purpose. We are very thankful for that. But last but not least, the greatest help the most sincere thanks to all my students who are involved in this project. There are 5 graduate students directly involved in this project. 3 previous graduate students are help us in supporting role, and we have 7 undergraduate students who got experience and research on this project. Thank you all for your kind attention. I greatly appreciated the opportunity to present at this symposium. Thank you so much.